Welcome to College of Science and Technology. This is the ISC module 201, and in today's session we are going to learn about the Hayes bridge. The Hayes bridge is used for determining the self-inductance of the circuit. The bridge is the advanced form of Maxwell's bridge. The Maxwell's bridge is only appropriate for measuring the medium quality factor. Hence, for measuring the high quality factor, the Hayes bridge is used in the circuit. In Hayes bridge, the capacitor is connected in series with the resistor. The voltage drop across the capacitor and resistor are varied, and in Maxwell's bridge, the capacitor is connected in parallel with the resistor. Thus, the magnitude of a voltage passing through the resistor and capacitor is equal. If you look at the construction of the Hayes bridge, the unknown inductor L1 is placed in the arm AB along with the resistance R1. This unknown inductor is compared with the standard capacitor C4 connected across the arm CD. The resistance R4 is connected in series with the capacitor C4. The other two non-inductive resistors R2 and R3 are connected in the arm AD and BC respectively. The C4 and R4 are adjusted for making the bridge in the balanced condition. When the bridge is in a balanced condition, no current flows through the detector, which is connected to point B and C respectively. The potential drop across the arm AD and CD are equal, and similarly the potential across the arm AB and BC are equal. We already know that the balanced condition of the bridge is given by the equation Z1 into Z4 equals to Z3 into Z2. So from here what we have to find is we have to find the value of L1 and R1, which are unknown to us. So since this is the derived formula, we will also look at the derivation of L1 and R1. So we also have something called quality factor. Quality factor is denoted by Q, and it's given by Q equals to omega L1 by R1, and we can also say that quality factor is the ratio of inductive reactance divided by the resistance. So we are going to derive the equation for the value of R1 and L1. Since we already know the general equation of the AC bridge, Z1 Z4 equals to Z2 Z3, upon substituting the values of Z1 and Z4, we get R1 plus j omega L1 into R4 minus 1 by j omega C4 equals to R2 R3. Upon multiplication, we obtain R1 R4 minus j omega R1 by omega C4 plus j omega L1 R4 plus L1 by C4 equals to R3 R2. Since this equation contains both real part and imaginary part, we are equating this equation separately. So R1 R4 plus L1 by C4 equals to R2 R3 is the real part of the equation, and j omega L1 R4 equals to j R1 by omega C4 is the imaginary part. So upon cancelling j on both sides and making R1 as the subject, we get R1 equals to omega square L1 R4 C4. Let's keep this equation as equation number 3. Then from here we are taking out L1 out, and after taking L1 out, we are getting omega square R4 square C4 square plus 1 divided by C4 equals to R2 R3. Now making L1 as the subject, we get R2 R3 C4 divided by 1 plus omega square R4 square C4 square. So putting the value of L1 in the equation number 3, we obtain the value of R1, which is equals to R2 R3 C4 divided by 1 plus omega square C4 square R4 square. So this is the derivation for the for the unknown value of L1 and R1. So this is the phasor diagram of the bridge, and this phasor diagram is obtained from the above circuit that was shown earlier. The magnitude and the phase of E3 and E4 are equal, and hence they are overlapping each other, and they are drawn on the horizontal axis. The current I1 flow through the purely resistive arm BD. The current I1 and the potential E3 are in the same phase and represented on the horizontal axis. The current passes through the arm AB, produces a potential drop I1 R1, which is also in the same phase of I1. The total voltage drop across the arm AB is determined by adding the voltage I1 R1 and omega I1 L1. The voltage drops across the arm AB and AD are equal. The voltage drop E1 and E2 are equal in magnitude and in phase, and hence overlap each other. The current I2 and E2 are in same phase as shown in the diagram. The current I2 flows through the arms CD and produces the I2 R4 voltage drops across the resistance, and I2 over omega C4 voltage drops across the capacitor C4. The capacitor C4 lags by the current 90 degree. The voltage drops across the resistance C4 and R4 gives the total voltage drops across the arm CD. The sum of the voltage E1 and E3 or E2 and E4 gives the total voltage drops E. Now let us consider the advantages and disadvantages of the Hayes bridge. So the advantages are: the Hayes bridge give a simple expression for the unknown inductance and are suitable for the coil having the quality factor greater than the 10 ohms. It also gives a simple equation for quality factor. The Hayes bridge uses small value resistance for determining the Q factor. The disadvantage of using Hayes bridge is that equations of L1 and R1 are very complicated, as it was shown in the derivation earlier. Next, the measurement of R1 and L1 require the value of frequency. So if there is no value of frequency given, then we cannot determine the value of R1 and L1. Similarly, this bridge cannot be used for measuring low Q factor, because it is only used to measure which has the Q factor greater than 10. So
Hello everyone, welcome to ISM 201. Today I'm going to solve problems related to his bridge. Here we have given the question: find the series equivalent inductance and resistance of the network that causes an opposite angle to null with the bridge arm, where given omega equals to 3000 radian per second, R1 equals to 2 kilo ohm, R2 equals to 10 kilo ohm, and capacitor 1 is given 1 microfarad and R3 equals to 1 kilo ohm. So first of all, we have the balance equation, z1 times z4 equals to z2 z3. So from this equation we will going to solve the uh, equation for the unknown uh, inductance and resistance. First of all, z1 is equals to R1 plus the impedance of this capacitance, and Z2 equals to R2, Z3 equals to R3, and Z4 will be equals to the R4 plus the impedance, uh, inductance reactance of the inductors. And upon substituting these values in the balance equation, we'll obtain R1 minus j omega divided by omega C1 times R4 plus j omega L4 equals to R2 R3. Here, upon substituting the values of the impedance in the balanced equation, we have obtained this this equation, and so we will keep the all real terms together and imaginary terms together, and upon equating the real terms, we got r1 r4 plus l4 divided by c1 equals to r3 r2 r3. So we will keep this as equation 1, and upon equating the imaginary part, we got r1 omega l4 equals to r4 divided by omega c1, and this implies r4 equals to r1 omega square l4 c1. So we will keep this as equation number 2. So then we will substitute this equation number 2 in equation 1. We will get r1 square omega square l4 c1 plus l4 divided by c1 equals to r2 r3, and so we will take l4 common here, and the take l4 keep here, and other parts we will take to the other side, and we will get l4 equals to c1 r1 r3 divided by 1 plus omega square r1 square c1 square. So we got the equation for the unknown inductance here. Upon substituting the values of R and capacitance and resistors in this equation, we will get the inductance 0.27 Henry. And for R4, we will use the second equation. This is equation number 2 is R4 equals to R1 omega L4 C1. So upon substituting the values of R1 omega L4 and C1, we will get R4 equals to 4.86 kilo ohm. So this is for our solution for the problems related to Hayes bridge. And thank you guys. Like and share our YouTube channel.